Cool. Okay. So we're gonna start.
Cool.
Okay.
Do you want to give me
Thanks.
a
Yeah.
one? Do you want to
I'm
tell me what
gonna.
the objective of this
Yeah.
is?
So
Okay.
my understanding of these talks is they're meant to be sort of, there are tutorials. So they're
Uh-huh.
meant to be like a dialogue where I'm trying to explain some ideas to you and you're trying to understand them.
Uh-huh.
And so that means that it is more of a dialogue.
Uh-huh.
So it's hopefully not me just ranting at you
Uh-huh.
incessantly for an hour and a half or whatever. And the idea is that you come away understanding what I was getting at,
Uh-huh.
and everyone else who's around also benefits from that, and everyone else can also pipe in as well, right?
Cool.
So,
Is there
so the
so
specific
what is the specific thing I'm learning
is
today?
that yeah, I have this idea that is, I'm just going to say like me, it's built, it's being fleshed out in a lot of ways by a lot of people here, in
Hmm.
particular Owen as well, but it builds on a lot of ideas, which I'll talk about, that are sort of already in use at Topos and have
Uh-huh.
been developed by the people who put Topos together, about how we can use categorical logic to assist in the design of platforms for some mathematical modeling in the sciences and industry.
Okay.
We're not going to get all the way there, but what
Uh-huh.
we're going to try and do is I'm going to try and tell you a sort of mapping between topos theory and modeling in the sense that we aim to understand it at topos.
Uh-huh.
So that's going to
Okay.
be, I'll write
So
that.
my summary here is the context of this is uh, understanding how categorical logic can be sort of like a conceptual underpinning for a modeling platform for complex systems or something like that.
Mhm.
And the particular goal here is to talk about topos theory, surprisingly. But even though we're at topos theory and how it relates to this sort of way of modeling.
Yep,
Great.
that's right. Okay. So, right. So I need to start with we have a number of particular ideas about what it would mean to be a categorical modeling, or sorry, what we dream of for modeling
Hmm.
platform and its capabilities.
Right.
And so I want to go through, I'm going to give an opinionated list of them, and then we're
Uh-huh.
going to like one by one go through and see that they have analogs that can be done with topos theory, and I'm going to
Nice.
try and describe how those work.
Cool.
And then I probably, so just based on your background, I will. So there's, topos theory. There's this idea of sketches of the elephant.
Uh-huh.
There's this huge elephant, which is
Right.
topos theory, and you can touch it many different ways.
Uh-huh.
And so I'm going to give you the more categorical point of view,
Uh-huh.
but there's also a type theoretical point of view,
Hmm.
and that's important because it's something that you could actually implement as a sort of
Uh-huh.
programming language. And that's the I believe we have Owen publicly talking
Uh-huh.
about geolog and EMTT, and I've been working with Mitchell Riley
Hmm.
on a thing called theory type theory, which
Uh-huh.
is meant to be a Martin Loff style type theory for this. So I think
Cool.
we won't cover those, and instead I'm
Uh-huh.
going to give you something that's more purely
Uh-huh.
categorical with ideas from there because I think it's going to click better.
Mhm. Is there a way I should be, you mentioned there's many different ways of thinking about what a topos is. And even within a categorical viewpoint, is there like a one sentence way that you want me to be thinking about what a topos is in this talk?
Um,
Perhaps not.
Yes,
Uh-huh.
but I think I want to lead into that a little slower
Okay.
than just starting you off with that.
Uh-huh.
So I'm going to start with with the ideas for modeling,
Uh-huh.
and then I will use that to inform how I want you to think about toposes.
Okay. Sounds good.
Okay, so the idea of we have this idea in modeling. So if you look at the design of Cat Collab, a lot
Uh-huh.
of these ideas are built into the design of Cat Collab. So here's my little like design of Cat Collab of Cat Collab, real and
Hmm.
aspirational. The window looks sort of like this. We have up top here, we have a sort of split that's like this.
Hmm.
And in here, up here, we have something which in there is called a logic,
Hmm.
but it won't be called a logic. One sort of theme of this is that everyone uses different names for different things, and sometimes they're the same names, but
You're right.
they appear in different analogs. But a logic is here something like, let's say, Petri nets or whatever. As in, this is what I will call here a meta model.
Hmm.
That's what a modeler would call it. Or like not a modeler, but a model
Hmm.
modeler.
Uh-huh.
The kinds of people who's thought about them, how you model the
Wonderful.
modeling process, so you
Right.
can design tools for it. And this would be the meta model. And then on this side, you would have what I could call the conceptual model. And this would be something like, um, and this would be something like you have, S is a species,
Hmm.
and I is a species, and infection is a transition, and we might write it as like S comma I to I comma I, something like this, right?
Right. So in particular, in this particular example, the meta modeling language, that is the way that the sort of conceptual framework or the domain we're talking about is PetriNet, which is some sort of model way of talking about concurrent systems. And then your conceptual model is a particular PetriNet, and this particular PetriNet is, um, I guess, talking about infection and disease transmission. And S and I stand for implicitly, I guess, for susceptible and infected.
Yes,
Mm.
totally.
Okay.
And
So
so,
why call this a conceptual model?
well, the reason this is a conceptual model is because we're going to distinguish it between what happens on the right-hand side of the
Uh-huh.
page here.
Okay.
So this is a conceptual model because it's sort of like it's something you could also call an ontology,
A
right?
conceptual model is an ontology.
Uh, yes, I will say that the word ontology could be used both also for the
Right.
meta model.
Yes.
So like it's not, yeah. So it's a little
But this is what you're saying that John Byers once said to me, like one person's syntax is another person's semantics.
right, right,
And
and
that's the part of the sort of layering of modeling languages, which allows sort of greater control over formalism.
right, right,
Mm.
right. And so here, like your meta model is already an ontology. It says there are things called species, and they relate through these transitions, and a
Mhm.
transition goes from a list of species to a
Right.
list of species. And then it may have more things, which will come out in the science as we do today. But the conceptual model of a particular Petri net is also a sort of ontology. It says there are
Mhm.
susceptible individuals, there
Right.
are infected individuals,
Right.
and a susceptible individual and an infected individual could come together,
Right.
and through a process called infection, you end up with two infected individuals, right? So
Right.
that's what's written on the left-hand side. And so that's a sort of ontological statement about how the world it's a concept, all right?
Hmm.
But what it is, it's also, you might call it also a qualitative
Hmm.
model. But then there's also what I'm going to call the practical model. Also in Cat Collab lingo, this would be called the analyses.
Hmm.
And so what is the practical model? Well, the practical model is some computation you perform from the conceptual model to understand it use that. And
Hmm.
now the thing to note is that the kinds of computations you can perform are determined by the meta model.
Hmm.
So in particular, I can do a mass action semantics here
Hmm.
where, I get, well, okay.
Okay, yeah,
But,
sure.
well,
Oh,
where I
in
can graph,
particular, susceptible people get
yeah,
infected over time.
yeah,
And
this graph is not to scale, it's like very fast, but
well,
not to no scale. And yeah, there's no shelf up there. Anyway,
uh,
the point is that you can learn qualitative things about that,
right.
I should
Hmm.
say, but I'm going to call this the
Hmm.
quantitative model. Right. And then one thing I'll say is that also we have that this thing here is an implementation. I might call this an implementation of the conceptual model.
In that you have to choose particular parameters of for like initial particular initial populations in these species to then get a particular view of what happens in when you instantiate the conceptual model with those initial conditions.
Yes, and also we had to actually write or pull in the library that had it
Mm.
written the code which actually simulates the
Uh-huh.
model or implements something which is described by the left-hand
Uh-huh.
side.
So something else you could do to sort of interrogate a Petri net as a conceptual is some sort of reachability analysis,
Yeah.
right? Which is not, is that still, does this language of like quantitative models and implementations of these models, does that still apply as the right way of thinking about that?
Yes.
Or are you just
So that
specializing
is also
particular case?
reachability can also be an implementation, and I'll go into why reachability is an interesting case here.
Uh-huh.
Um, for because it can be expressed in a restricted with a restricted kind of computation.
Hmm.
So reachability is also a what you could is a way of implementing this in the sense that we actually had to write the algorithm that
Hmm.
finds tests for reachability.
Hmm.
And then I'll also note another thing that you might say is that the specification, if you had it, if there was another line here, right? The specification for safety critical systems, you might have a specific.
Okay. Yeah.
There we I lost it. The
Yeah, it's
spec.
bad.
That's
Right.
why. The spec of the model would be something else. You would put conceptual. It's something we want. It's
Uh-huh.
sort of it's something we want about the model, and
Right.
it's expressed in conceptual terms, right? But then the certification is again something that we compute about the model.
Right.
So this is this idea, and then there's a few other desiderata we have.
Hmm.
So we have this left-hand side and this right-hand side, the conceptual model and the practical implementations of the model, and we actually make a strong decision here. That's part of our sort of approach to declarative modeling, or as Owen likes to say, models as structured data,
Hmm.
right? Is that the conceptual model we aim to separate out from the implementation,
Hmm.
and there's a reason to do that, and it happens to do with this distinction here. The left-hand side is data, or
Hmm.
maybe even presentations.
Hmm.
It's a presentation of something. And the
And
right-hand side is a general computation.
um, okay, I can probably
And
draw this. Sorry, I'm still
so
learning to use
general.
this tool, but there we are. Um, so by presentation, you can also present things with equations, I presume. It's not just
Yes,
free
yes,
presentations.
that's right.
Um, and a specification, what is the specification language? Is it the same, like, is there a choice being made there of some sort of logical language or something like
Yes,
that?
yes.
And that's simplistic?
I'm not gonna really cover that. So like, well, I'll say this as save for later.
Okay.
We have enough to we have
Yeah,
a
this
lot to
is a
go
lot.
through, and I think I'm gonna save this for later. But I'll uh yeah, so
Right. And
I'll say
that,
that when the spec is written in a syntax,
mhm,
and that syntax forms basically it's another meta model,
mhm,
right? And then the certification, however, is checked using general. So that syntax could describe something
mhm,
that is of a sort of a a general form of predicate,
mhm.
and then you would certify it by actually trying to solve for it or check
Right.
if it's true through
Right.
whatever means.
Right.
And
So-
I will come back to that a little bit, but it will be helpful to do. It will be helpful to do once we've established some of the connections to the topos theory, I
uh,
think.
so another form of computation you can do on like some sort of conceptual presentation of data is just like is trying to transform the syntax. So you might do a visual presentation
That's
and
right.
present a bit. Is that so that lies on the right hand side. When you talk about like a quantitative
I'm going to
model,
call
is
it
that
translation.
translation, right? Do I still think of it in this pattern of being quantitative, or is that distinction there not?
We will find that there is a sense in which translation, maybe I should put like translation. Well, it's not that it doesn't, I don't want to make it look like it goes between these things, but
Hmm.
translation is somehow both of these at
Uh-huh.
once. It's on the going to be on the left and the right, and I'll make precise when in the like I'm guided here, of course, by
Uh-huh.
my analogy. The topos theory I'm trying to
Uh-huh.
make real, and in that way, you'll see that the translation is both something that I could describe on the sort of left hand side and the right hand side. In particular, it's sort of precisely those things on the right hand side, those implementations or analyses that in fact concern themselves with presentations.
Okay.
Yeah,
So this perhaps gets at my last question, which I think is taking us a bit further afield
yeah.
from like where you're trying to go. But just to sneak it in quickly, you can imagine that the computations reveal aspects of the qualitative model, the data presented.
Hmm.
Uh, you might also imagine wanting to work with the data from the viewpoint of something, some view that has been computed out of it.
Yeah, yeah, yeah.
And how do you think about
Going
that?
back
Yeah, going back. Like
and
for example, one way might be you manipulate a translation, like a visual presentation. You change the names or something, and that should go feedback to the conceptual model. And another is you might say try and when you have a simulation like this, like these sort of graphs you've drawn of the S and I curves over time, you might want to sort of try and say, right, put some sort of predicate on that and say, okay, that being the case, it's now revealed to me that I want to sort of make some sort of specification
Yeah.
of these bounds of behavior and see whether that holds over all things.
Yeah, there's a
Um,
field of computing science called bidirectional
right.
transformations,
Okay.
which talks about this a lot, and I do think it's really interesting. It's not something I'm going to be able to come to
Okay. Cool.
in this talk. I do think it's a very important part of the idea. But let me just
Mm.
say, like, to a partial point of that,
Uh-huh.
like, so one of the things I want to say is that we have something like we have Petri nets, and then like in between this transformation here, right? How do we go from the Petri net to this graph, right?
Hmm.
Well, one of the first things we do is we take the Petri net and we're going to turn it into a system of ODEs.
Hmm.
And it's ODEs are equations, and as you said, equations could be present ways of presenting
Hmm.
systems, right? And then we take that, right? And then so this is
Right. That's true. Yeah.
translate via the rate equation, right? And
Mhm.
then we are going to solve here.
Right.
And we'll see that and solve here will produce like an actual, this will be some actual, I'll end up here that will end up no longer, will end up in this sort of empty meta model, as in we'll end up with base types or just like actual
Okay.
quantitative things that or that escapes our modeling platform. I'll come back to this idea as we start to connect to the topos theory,
Hmm.
I'm going to have to pick. I'm going to have to sort of when I say topos theory, I mean Grothendieck topos theory,
Hmm.
and Grothendieck toposes are all defined relative to a special category, which is the category of sets. And we have to pick what we mean by the category of sets. The notion of set is sometimes mathematicians don't attend to this,
Uh-huh.
but it's been well known for a long time that the notion of set is extremely underdetermined
Hmm.
by formal logic, right? So it's better to pick an attitude to what we mean
Uh-huh.
by sets than to actually say, oh, we're trying to talk about some real thing in the world. I know that there are some philosophers who take that
Hmm.
position, but I don't. And I'm going to take the idea that what a set is for us is going to be the programming language in which we have written our modeling framework. So the
Wait,
meta
what is
meta
a
meta.
modeling framework? Can you
The
just,
ability to the system that lets us do all these operations and computations and whatever that we
can
do.
you give an example in this, like, yeah, the whole thing, there are models everywhere, right? So
Yeah,
you're saying
yeah.
the programming language in which, what is the programming language and
Right. So
what does that
yeah,
have to
let
go?
me maybe write down a list of things that we want to be able to do up here, right?
Mhm.
So we want to be able to, and I'm gonna bring up one I've
Wait,
cooked
okay,
earlier. Yeah,
before
yeah,
you
before
answer
we do
that,
that,
maybe
yeah.
I can ask a more specific question. So you're saying the PetriNet is a logic in terms of for the conceptual model in this example, but then
Mhm.
you're saying there's also logic of ODEs that is,
Yes.
and you translate into that logic as we move
Yes.
across to the practical modeling
Yes.
side, and that is the sense that also want to formally track the fact that you're working within that logic. And in fact, what is the logic of ODEs? Is that
So I can give you very explicit examples that are due to Bob Atke
uh-huh.
in his little note on lambda dots, which is turned into a small library called a gate by Obsidian.
Hmm.
And I can show you explicitly what it is, but you should think of them as resource sharing ODEs.
Okay.
They share variables,
Uh-huh.
and when they do, they add the
Okay.
derivatives of those variables. So
Do you have an idea of what is the sort of meta model? Like when that sort
yeah,
of this language of
topos.
OD is topos. Okay, great.
That's what I'm going to try to
Okay.
argue here.
Great.
So and I would say also like there's the idea is to do a type theory, which
Mm-hmm.
is you might think of as a programming language that in which all of these things could be type checked and expressed.
Uh-huh.
And so then there is the meta level, which is that if you implemented such a thing, you did
Mhm.
it already in a language. And
Right.
this is not the kind of thing that gets bootstrapped,
Right.
okay? Because we're
Uh-huh.
not really aiming, I would say, to do a system of general computation. We actually at some point want to say, like, look, we're taking our hands off, we're going to ship it over to the numerical solver
Uh-huh.
people, and they can do their magic,
Right.
right?
Right.
And so what is that language?
Mm-hmm.
That's going to appear for us as the category of sets,
All
roughly
right.
speaking.
Okay.
Um, so okay, so this is our modeling desiderata here, modeling the link. We need to be able to express a few things, right?
Yeah.
So we need to be able to we need to be able to express our meta models. Meta model.
Mm-hmm.
Wow, I struggling today. Um, yeah, yeah,
Yeah,
meta
tablet handwriting
model.
and paper handwriting and then whiteboard handwriting and so forth. They're all different.
Very different.
It's
Meta model, right? Now we want to be able to translate between meta models. We want to be able to describe actual conceptual models, right? We want to be able to implement models.
and this is the right hand side of the pane above what you're talking about,
Yep.
electrical models. Yeah.
Yep.
Mhm.
And yeah, and then we want to be able to do, we want to be able to do general computations, understand what they are, computations on models, about models. This is part of what it means to implement them.
Mhm.
And I'll call this thing an implementation. And then also I'm going to talk about specification and certification. But again, if we're going to drop anything, we're going to drop that last one. Okay. And then there's also some other things we really want, which is we want mo conceptual models. We want to have modularity. So we want or compositional. We want to be able to couple, and compose models.
And
This
that's
is a
within one meta model. So coupling, compose, and
within a
taking
given
that.
meta model.
Mhm.
And so right. Right. Okay, so now I'm going to start working our way to the topos theory.
Uh-huh.
But before I do, I want to note that these ideas about modeling I'm talking about are my understanding of what the sort of what's in the air at topos, and that air has been, I don't know, I'm running out of my metaphor here, but David, Evan, and everyone else
Uh-huh.
at Topos have had a lot of thoughts about how this works, and one of the ideas is at first that there's a lot of overlap between what's going on in the world of modeling and what's going on in the world of relational databases.
Mhm.
So I want to start off by saying something like, I'm going to tell you a relation this to databases because it's going to help us because if you know about David's functorial
Mhm.
query language and functorial databases, that these concepts are a direct extension of that.
Mhm.
So in there, the meta model is really you're going to take your form of your schema. So that's the one that would take the
Mhm.
what David would call the ontology, not what I
Mhm.
call the other one.
Yeah.
I again I think that the you will note that sometimes there's a tendency to level shift in
Mhm.
this, which is I think unavoidable and something
Right.
that I don't think I have a really good story about yet.
Why it's unavoidable?
How to do it smoothly, how to handle
Mm.
level shifting smoothly. But that's neither here nor there.
Yeah.
Let's just talk about
Good
what I'm
question.
confident about for now, if
Uh-huh.
that's okay. All right. So schema, then now a translation. I'm going to do you have a guess of don't look at my notes. Do you have a guess of what a translation would correspond to? Could we go? I'll tell you this. We're only going to go this far for
Uh-huh.
databases. So um,
I mean, so
a
I'm
translation
curious.
between
I presume
schemas.
it's a functor between like schemas or
Yeah,
something, or
it's a
mapping
function
between
between
schemas.
schemas.
Yeah.
However, I'm gonna say that there's an interesting thing here, which is that what a schema. Well, we're gonna make a pit stop along this, but I'm gonna try and talk. I'm gonna tell you the topos idea, and then we're
Mm.
gonna work through it. Once I've laid out the analogy, we're gonna jump into the category theory, and it's gonna become a lot more concrete from
Uh-huh.
that side, like
Mm.
abstract nonsensically concrete.
Uh-huh.
Okay, so I'll just tell you
Formulaic.
what
Yeah.
this what I'm saying here is that this is going to be an instance, and the reason this is going to be is because of what we'll take schemas to be, and we're going to take schemas to be much larger than O-logs or
Mm-hmm.
categories. We're going to take them to be something more like sketches of a
Mm-hmm.
particular sort. And the idea of an instance of a database,
Uh-huh.
the reason I would think of it as a sort of translation is, remember, a translation takes a presentation and turns it into another presentation. And
Hmm.
so the idea is that for anything in your schema, you're going to have to say, how are you going to present a bunch of data
Hmm.
about that? So the thing to remember is, up above, we had this big
Right.
distinction between data on the left-hand side and
Hmm.
computation on the right-hand side,
Uh-huh.
which I'll come back to. It's very central.
Uh-huh.
And down below, we're going to see that again. I should say that this is data and this is computation down here. And down below, right, we'll see that again. But the thing is, an instance, translations are all about data, and this is an instance. I'll come back to why this actually makes sense, and it's
Okay,
going to
yeah,
be a little
I'm
confusing.
not
Okay, and then
not
I'll
comfortable
I'll,
with
I'll
this
say
yet.
that this is going to be a monotonic query, and that's weird. I think this is weird.
This
This
is
is
all quite
not
weird
how.
to me,
This is weird.
right?
I know it's a little different than the normal one because you probably expected me to say something like model. So we have another column,
Right,
which is
expecting the
logic,
next one
and
to be instance,
right.
right? And so I presume this is wrong, but do I interpret your notion of translation as instance, meaning that it's a translation from a sort of database over, yeah. Uh, like,
All
are we talking about a sort of an instance also over the empty schema or something like that? Is that coming
Yeah,
into
it's an
play here?
instance over the empty
Right.
schema. Sorry, an instance.
Yeah.
So sorry, if you have a schema, an instance of that schema is going to be a bunch of data.
Hmm.
So it's going to be a functor to set. But as you'll see, we're going to make a strong distinction between what are data sets and what are general computation sets.
Uh-huh.
And we'll come back to that. I'll come back to this when I talk about topos theory. Really, it's really
That,
central.
can I think of
So
this
yeah.
example in this context, or shouldn't I, is that misleading? Like, so here I have a Petri net.
Mhm.
I could think of it, a Petri net is the language of Petri nets is my meta model. So that's,
Mhm.
I could think of a database schema for Petri nets, the
Mhm.
Petri net has species and blah, blah, blah. And then an instance of that schema is a particular Petri net. But that seems to be, in your example above, that seems to be a conceptual model and not a translation.
So this
What's
is
going on
translate.
here?
This is compute here. It's not a translation. Um, the maybe I'll just keep going,
Okay,
and
sure.
because I do think this is confusing. Actually, I probably shouldn't have started. I probably shouldn't have written this column here.
Okay,
Um,
cool.
let's just do toposes.
Yeah.
So this is
And
the
sorry, one last question. When
yep.
databases, you really do mean relational databases? Because, graph databases
Yes,
also have a
I
notion of schema
I mean
in one
relational
functor.
databases.
But
Or really, I mean like functorial data. I mean like David Spivak's functorial database.
okay.
I mean like
So
that's the
in
way you think
particular,
of
sort of
databases.
some sort of like categorical data model
Yeah,
underlying your database.
categorical data model. That's right.
Yeah.
Okay, so in topos theory, we're going to make the following associations. We're going to take each meta model to be associated to a topos. We're going to a topos, but it's going to be in particular a topos of sheaves, right, on some syntactic site. So what is this is something that's fun to know about
Uh-huh.
every topos. So I'm going to put another column. We're going to
Hmm.
call this logic.
Hmm.
This is going to be a notion of a theory, right? But it has to be, we'll say this, strictly positive, aka geometric. A geometric theory, aka strictly positive theory. Okay. So if you have a topos, so by the way, every topos is a sheaf on some syntactic site. So this is, I haven't changed the meaning of the
Hmm.
generality of this. I just want you to think about it that way.
Uh-huh.
So
As a syntactic site, do I think of that as the schema? And why, yeah, or not?
the yes,
Yes, okay.
exactly. So it's perhaps better to think of the syntactic site as the schema
Hmm.
itself, and
Okay.
the top we're going to use them using the toposes. If we just use the syntactic site and stuff like that, we could only get the first three column, the first three
Okay.
rows. By using the topos in addition, we're also going to, and this is actually the precise way. When you ask me how should I think of a topos,
Right.
what you should think of it as it's the completion of the schemas
Mhm.
with types corresponding to general computation.
Okay, right.
And this is what is extra about using topos theory and
Mm-hmm.
why we can nicely handle both sides of the Cat-Collab window and not
Mm-hmm.
just the pure data modeling part. I feel like I've read a lot,
Yeah.
but I think I'm maybe going way too high level
I
here,
mean,
and it is a little confusing.
but
Uh,
perhaps analogy here is the shift between like directed graphs and categories or something. The category is the completion of the directed graphs. We can talk about the paths as sort of first class objects.
yes, exactly. So that's why a topos of sheaves on the syntactic site. The schema itself is going to be like the syntactic site. So
Hmm.
we have this sort of comparison here between this and the syntactic site. And that is a syntactic site generated by this theory. So you could also think of the schema as being a theory.
Hmm. Right.
Um, and then, so that's the way to think of it. The topos is something that is presented by that, and it's presented precisely by allowing you to do general computation.
Right.
So I'll come to that in a
Hmm.
bit. Right. So now an instance here is going to be a map of classifying sites of syntactic sites.
Right. Yeah.
Sites.
Still don't see why that's an instance, but carry on.
Okay.
Stop asking about this.
Yeah, I know it is a little weird.
Uh-huh.
It is a little weird, but the thing is that we're going to control the fragment of logic we use, and you'll start to see that the syntactic sites end up having a lot of sets in them, a lot of objects in them, and that's why um, you end up like so
But
you may be familiar with if C is my schema,
uh-huh.
you may be familiar that an instance is something into
Well,
set,
that was what
right?
I was just about to ask.
But
But that seems
instead
like a
of
sheaf
this,
on
yeah,
the syntactic side.
right. But it might be worth noting that set is fam of a point. In other words, the
Mm-hmm.
free coproduct completion, infinite coproduct
Mm-hmm.
completion of a point.
Mm-hmm.
So this is in fact the empty theory
Mm-hmm. Right.
in some setting.
Yep.
And that's the sense in which you should think of this as
As
an
a
instance. It's a map between, yes, indeed,
uh,
this is a map on syntactic sites here.
but it's okay, okay. Yeah. It's
The
usually
idea
means
is
you've
usually,
chosen a
in fact,
particular site that it shows
usually, in
special
fact,
properties of
when
the
you
data.
look at this, yes, you could go to all sets, but
Mm-hmm.
in practice, your data is not all sets.
Uh,
It's sets that can be actually stored nicely in a computer.
okay.
And that's a very different kind of set
Uh-huh.
than other types of set. And this is
Mm-hmm.
a thing that we're going to go through over and over again here. It's the most
Okay.
important distinction. It's a fundamental distinction in topos theory between data and computation, also known as logic, as this is polarity. So this is positive, and this is negative polarity, the concept from type theory.
Sorry, I lost the
Um,
image.
and I'll just say,
This one. Okay, I'm
yeah,
gonna go up again. Where did you
preempting
write
any
that? Okay, you're writing off the screen, right?
slight.
Okay.
I don't know. I guess my screen's really wide.
Yeah, my screen
Okay.
is not that wide, so maybe
Okay.
stay
I'll
up.
try and
But
stay within
do you
the.
want to actually just looking at this? You want to just write that again
Yeah,
and
yeah.
make
I'll
this
just. Can
visible?
I grab it and move it in? Whatever. Um, I'll just write it again.
Mhm.
Positive. This is maybe I'll write it on the other side because it makes more sense to write it on the other
Okay.
side.
But I did manage to move. Oh
It's
no,
okay. It's
sorry.
okay.
No, okay. No, I'm
I'll put it
terrible.
here. I'll put
Okay.
this is called positive. So
Right.
it's next to the it means the same thing as this. So I should put it next to it, and this is
Okay.
negative. And this whole thing is called polarity. The
Mhm.
distinction between those two is called polarity in
Right.
type theory. So right. So the main uh so I'm sorry that this is a little confused. I haven't done any
That's fine.
prep for this,
Yeah, yeah,
and
yeah.
this is
Yeah.
but I'm
Work in
trying
progress.
to
That's the point.
it is. And I'm trying to get the idea. So we're gonna see that like so one thing I will say, right, is that if we're going the schema that corresponds to the empty schema,
Hmm.
as in we're not assuming anything,
Hmm.
its topos will be the category of sets.
Hmm.
All right. And so
Hmm.
we'll come to see what that is. But its syntactic site, again, it's really going to depend on what fragment of logic we're going to look at.
Hmm.
I'm going to focus on the so-called lextensive fragment. It's not a
Hmm.
fragment of logic, it's a fragment of positive type theory, but that's
Hmm.
okay. We're going to focus on that because I think that corresponds really nicely with the stuff that's already been done at topos.
Hmm.
And in general, we can use bigger, we can do more if we want, or less,
Hmm.
or various other things. Okay. So an instance will be a map of the syntactic sites, and a conceptual model will actually be an object of the syntactic site. And this
Fragmented.
is different. This is really different than how most people how we have thought about it in the past. And it's something I only realized when writing up that little note for you last Friday or whatever it
Hmm.
was. um, so the um, the point is again that the conceptual model is data, and we need all that stuff to appear. The syntactic site is it's being syntax really does mean it is all about data. So the conceptual, so this is why it's up there. So an object, so we're
So
gonna,
object of the syntactic site and
yeah.
not an object of the topos or sheaves. And that is not a sheaf on the syntactic site.
So or representable sheaf.
Okay.
So yeah,
So query, okay, this is a conceptual model, which is a query. So just to go back to the PetriNet example, there is some syntactic site, which I think of as the ontology of PetriNets, but I can equivalently think of that as the topos of sheaves on that syntactic site, which is the topos of PetriNets. And then anyway, I'll skip past instance. Then the object, like that's a somehow what I guess what are the non-representable sheaves in this topos?
let's talk about that, right?
Mhm.
What are the non-representable
Oh wait,
sheaves?
sorry.
Yeah.
But in the Petri, I'm coming to questions as I go through the example. So you're saying every PetriNet, I can define a syntactic site. Maybe I
Yeah.
can't, but
Let
I can define a syntactic site which represents PetriNets.
yeah.
And then the PetriNets themselves, any PetriNet I can draw or present,
Yeah.
that is an object of that syntactic site.
Yes.
Fascinating.
Yes.
Cool.
And so I'm gonna I have a I think a rather nice like two algebraic approach to this that makes it look less daunting, at least for me, through all these concepts that of topos theory that are based on sort of the paper of lexical limits by Lack and Garner. Um, that I would like to tell you about right after this, or
Hmm.
maybe now. But
Uh-huh.
like the thing I want to say is that basically, like, yeah, so you can think of these as I'd say topos. I'd say, but you could think of this as being um uh this is you really could think of this as just being a syntactic site. Like this is maybe the better way to think of it. And then in computation here, I'll call this a morphism of sheaves.
And then by syntactic site, you just mean site.
Yeah.
Yeah.
Yeah. Well, yeah, I still do want you really want to think of it.
As the
You're trying
syntactic
to
site.
actually do this in a way that you could actually like make it into a computer system.
Uh-huh.
And so you really want to think of it also with logic or type theory.
Hmm.
And in this case, you do have this theory that you build the syntactic site out of, and
Hmm.
also
Right.
you're fixing a fragment of logic to make this make sense.
Okay.
And the idea is that the fragment of logic is roughly speaking fixed in advance, or maybe it can be controlled through the course of the system because it actually determines what kinds of translations are allowed as well.
Hmm.
But the idea is, I would say, so I'm sorry, this is getting a little wild here, but I should go. Maybe I'm just going to start telling you about type. I'm going to start telling you about the mathematics of this, and we'll
Hmm.
match our way back up. So I'll just finish up the table real quick,
Yep.
which is implementation is going to be a geometric morphism, and that's what is going to be a model of a model in logic. And note that it's not where we put the model there, but it's sort of our practical model in logic.
Hmm.
Um, and uh, uh, and then we will note that every so in i.e. a computation lives in the sheaves on, if this is our syntactic site C, this lives in sheaves on C, the topos. So I'll
Okay.
talk about that. Yeah.
Sorry, I noticed
Sorry, this has gotten a little.
I guess I didn't, I noticed I'm not quite clear on the distinction between implementation and computation.
Um, right. So let me do some math now because I think the more I talk vagaries, the more
Okay.
likely we're going to. How do I make a new page or get more pages? Maybe this button. There you
Yeah.
go. Okay.
Okay. And then how
Okay.
do I find a new
So
page? Do I just keep scrolling down?
yeah,
Here we are.
now are we lined up here? Yeah.
I think
Okay.
so.
That's
The
pretty
top of
good.
the page. Yep.
Okay. So right. So okay. Um, so one thing is that like if you let's do a little review of 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 yeah, let's do a little review of things. So we have a category C,
Hmm.
cat C. We can think of this as an O-log, right?
Hmm.
So its objects are sorts of things, and its morphisms are yeah, sort of relations. One thing has another thing or relates to another thing,
Hmm.
right? So then we can form its lex completion, L of C equal finite limit completion, lex completion equals, right? It is going to be, we take the finite limits of representables, representables on C op,
Sorry. Um,
right?
distracted with something. Where is your microphone? Oh, there.
It's right
Okay.
here.
Okay.
Yeah.
Oh,
So,
that's great.
right.
Mm-hmm.
So what are these, right? So the thing is, they're, sorry, finite colimits of represent. There we go.
Hmm.
Better.
Hmm.
So one thing is that this in David's ideas are these are finite conjunctive queries. Queries on in the O log C. And why is that? Well, if an instance is C to set, we're using this again, I'll tell you, like I'm going to refine this notion eventually, but like we're now going to use David's ideas
Okay.
here.
Okay. All right.
If an instance is C to set, right, then a finite conjunctive query is so first of all, we note that a representable representing this, like C this to I by Yoneda corresponds to IC.
Hmm.
So in other words, we can think of each object as determining a query, and that query says select C from this thing, right? Select everything that has this, right? So we think of this object on the left-hand side here as being a query, as acting as a query, and
Hmm.
to solve the query is to map out. And we see that the solutions of the query given by the representable is just a item in the database. This is an instance of the database, a log schema instance, right?
But the point is that like finite credits of representables on CL are just instances, right?
They are special instances, but we're not going to see them that way. So the thing I want to understand is first, a representable by Yoneda. A map out of a representable I corresponds to an element I in IC, right? So in other words, if C is a column of our database, right?
Hmm.
Then what we're doing is we're selecting everything from that column, right? But now let's suppose that I wanted to say select all things from column one, so that would be this one to I, and all things from column two, right? That have the same value on column three via some foreign key
Hmm.
from C1 to C3 and C2 to C3.
Right. So that's an
Right.
object in the code of the Lex completion.
Yeah. So this is the same thing as taking the push out here and asking for a map out here, right? That's the universal property of the push
Hmm.
out.
Hmm.
And what we note is that the result of mapping in here, right?
Hmm.
The maps from the push out, so push dot 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 into I, that corresponds to the limit of of the dualized diagram. IC1, IC2, IC3. Now the maps go this way, so it corresponds to this limit.
Hmm.
And so what you see is that like this is the sense in which, so what is that limit? It's going to be the set of all
Right.
I1, I2,
Hmm.
um, I3, such that I1 restricted to C3 equals I2 equals I3 equals I2 restricted to C3. Right? So the point is that this is a finite limit here because we were only
Hmm.
taking finite colimits, finite limit, and it's a conjunction of equalities.
Hmm.
Okay,
Hmm.
cool. So now we're gonna make our first thing is that like also we might want to include finite conjunctive queries, FCQs, into our schema, right? We might want to assume our schema what is instead of just being a category, something like a finite limit sketch. And the reason for doing that is that saying like you're allowing to have a finite key that is that points out of a finite limit of the things you have.
Hmm.
So this is nice if you want to define, so for example, a binary operation. You say you have a binary operation is a map out of a product,
Hmm.
but you can't form a product in just a category. You need to
Hmm.
also add the product in.
Hmm.
So we're gonna change our schema from just being a category to being something like a Lex category. So Lex is going to be the two category of finite limit categories. And we see that any category actually induces one of these. And in fact, they're going to have the same instances. Um, uh,
So it induces this by this finite limit completion.
exactly. By the universal property of the finite limit completion, they're going to have the same instances. And we're going to work our way back to, again, this is not the use of instance I gave in the above table, but we're going to keep going until we get there.
But
This is something,
okay.
yeah.
But they're not equivalent notions in that, not every Lex category is a free one.
No, not every
Okay.
Lex category is a free one. This is genuinely a stronger meta ontology,
Mm-hmm.
or like this is a stronger doctrine.
Uh-huh.
Um,
When you say a query is a representable, I'm still not, is that coming from somewhere or is that just a
yeah,
misdefinition?
no, David, this is part of David's lore.
Uh-huh.
I don't know where exactly to cite it from, but this is part of David lore. That's not me,
And
David. That's David Spivak.
yeah, and a query is, but you're saying it's just an element of an object as some
The
like
point is
what
that
do query I mean
a
is that
query
really
is
what a query is?
a query
You're
is
just selecting
a
something in your
query is
database.
more like the predicate. You know, you have some predicate concerning some finite numbers of elements, and it's a
Uh-huh.
finite conjunction of equal. It's a Horn predicate, right?
Uh-huh.
For example,
The thing
and
you wrote
you're
as like query and the that's a special kind of like representable query. And
that's a
it's
representable query. The point
Okay,
is,
okay,
maybe
okay.
I should
So,
start
so
with
okay, so
a
you're
query
only
is something
your
like
plain OLOGs, which are
yeah,
just finite presented categories.
yeah,
You define a notion of query for them, but that's actually a really restricted notion
a
of query.
really
That's just
restricted
find
notion.
me a thing in the database
Yeah, yeah,
with like yeah, find me a table or
yeah,
something,
yeah, yeah, yeah,
or
yeah,
find me a column, yeah, yeah.
yeah.
And you're saying like so most people don't use that word query for something so restricted, but that is a possible if
It is a
yeah,
possible
yeah,
query.
yeah. But you're saying
People would
let's
use
move to
something
a setting,
that are finite conjunctions
right?
of queries involving those
Right.
inequalities and
And so you
have
can
yeah
talk about that in the sort of free completion, like finite,
right
Lex completion of a on a sort of plain schema.
right.
Mhm.
But another
Um,
thing I want you to note
uh,
about this that's also interesting, right, is that in fact they are these finite colimits of representables.
these.
The finite conjunctive queries are these finite colimits of
Mhm.
representables, and so they're also something like um, uh, things you can uh, they're also something you can build up with finite operations by gluing things together. Right. So the point is that the query is something like this predicate that you have over here, that is slightly off screen. Sorry.
Sorry.
And then what we build is from that, we build this push out of this thing, right? And that push out is an object, right? It's in fact an instance, a database instance, as you pointed out earlier, Jason. This is a database instance which represents that query. But it's also note that this is a finitely presentable presheet. It's given by a finite colimit of representables. And so this is actually something that is, if you were, say, writing down something in the left-hand side of Calculab, this is actually something you could write down in that OLOG, in that schema. Where we're not using the cat code, like we're taking the schema to be the logic here. So for example, let's say if you have the schema for graphs, the finite conjunctive queries in the schema for graphs, the theory for graphs, where C could equal like this category, right? Source and target. The finite conjunctive queries for graphs are precisely the finite graphs.
Precisely the finite.
Where they like the query is like instances of this finite graph
Yeah.
in your other graph.
You're selecting from the query a finite union of a finite conjunctive query, excuse me, is in the theory of graphs, which just has these equalities in source and target. All you can write down is give me so and such edges that have some equation.
With the edges.
And that whole thing determines a little graph that is the minimal solution to your query.
Right.
And in fact, it's every instance of your query is an image of that universal one. And so this is a point to note is that the objects of LC, right, are finite conjunctive queries, but they're also the conceptual models in that logic, in that schema. And that's where we're just if you scroll back up to the big table,
right.
we're just looking at we're looking at the first three lines, and we have the schema here, right? Which we're now taking to be L of C. So I'm trying to argue is sort of the same thing. It's also the same thing as this query. The conceptual models are these queries that are there, and the meta model is given by this schema. As we talked about, the schema was originally a category, but as I mentioned, you could buff it up to the lex completion of that category without. But the useful thing about buffing it up to the lex completion now is if we look at what is an instant, well.
So okay, well,
so let me.
So it seems like you said a very important thing, which is that there is a stronger than one-to-one correspondence, but let's just say one-to-one correspondence between queries and instances of your schema.
If your schema is something like LC, right? So, right, back all the way back down. Sorry. Then an instance was going to be a map into set, a lex map.
Right.
Right. However, let's say that let's just consider the idea that we in fact are going to.
Oh wait. Okay. So no, I have it. It's not quite the same.
Yeah.
So in this particular example, saying there's graphs. Your graphs could be infinite graphs, but your finite graphs are the queries.
Yes. Yeah. That's right.
Yeah. Okay. So it's not quite a one-to-one.
Right. And that's exactly the difference here. The models of the theory of graphs are potentially infinite graphs, but the conceptual models are the finite graphs in this setup.
Okay. And so you're saying,
and we're going to keep expanding our doctrine until we get right. Because let me put it this way: you could have a graph, right, where every node is a function, and every edge is another function. And to compute the source, you have to do a general computation involving like maybe it's a stream of data that you're waiting from, and you have to wait for so long to get it. And it's like some real actual computation has to happen there. That's so different than the description of the Petri net we had above, where I say, actually, I'm going to lay out for you this whole thing, finitely present this whole thing for you. And we have we have these basic entities, and we have these basic relations between them. These are fundamentally different ideas. So infinite graphs, it's important to note that infiniteness comes in many different flavors, what it means to be infinite. And so
Right.
the distinction I want to make here is between these, between positive and negative types. And positive types are in other words, inductive data types
Right.
are data,
Right.
presentations of data. Yeah, finitary positive types. Strictly positive types. And then negative ones can be general computation, and those are infinite in this really strong sense, in the way, for example, that the functions from the natural numbers to the Booleans are like qualitatively a different kind of infiniteness than the natural numbers are, right? Um, not just because they are not bijective, but in fact because there's a liminal sense of topology and cohesion in the functions. They are revealed through time, in some sense, as opposed to being stored in a single location, uh, as a as a like serialized piece of data.
Oh, that's fascinating.
Okay, so okay. So yeah, sorry, let's keep going. I'm gonna maybe go even full new
Another
page,
new page?
maybe, yeah, or
Okay.
like a full, yeah, right down, right underneath it.
Okay,
Yeah,
just
there you go.
saying.
Yeah, something like this. Okay, so I'm gonna give you here's my like opinionated intro to topos theory. Okay, you ready?
Yeah.
So we have this two category Lex. We're gonna just leave the above story to like put down a little basics and then come back to it, right?
Okay.
We have Lex. Lex is this two category, right? And then the thing to note is let P of C be free co-completion. So, i.e., C op to set, or set to the C op, however we want to, right? Um, if C is small. But the reason to use free, small co-completion, set co-completion, whatever. Um, so so the free co-completion in general is the subcategory of presheaves that is given by small colimits of representables. So if C is large, it's not actually not set to the C op, but it is. But if C is small, it is.
Okay.
So normally you only hear set to the C op, and you can basically think of it that way. But the nice thing about this is the free small co-completion is not hyper large, right? And it has all these other. It's in fact always a topos. And well, that's not true. It's okay. That's not forget what I just said, but it's very nice, and in fact, it is P gives a monad on Lex. So as we know, it's sort of in a special thing that the free set small code completion actually already has finite limits already, no matter what you are, basically. But moreover, the functorial aspect works like this. So here's the monad. To be a monad, it suffices to give you a lifting operation, right? I need to give you the unit, by the way, is Yoneda. And I need to give you a lift to make it a monad. So for F, I need to give you a lift. And there is a canonical choice, right? Which is we note that this is, by Yoneda lemma, this is fully faithful. And so we can take the con extension, the left con extension here.
I think the error is the wrong way.
The left con extension here, and note that because unit is fully faithful, that's actually an isomorphism, and this gives us a lift, and this actually determines a monad structure on P.
Okay.
So that's how we do the functoriality then. So in general, well, this is not P of F, that's lift F of P, right? Right. So this is sometimes known as F to the P, whatever your monadic lift is, and in general, P of F is defined to be the left con extension along Yoneda of Yoneda after F, if F is from C to D. And in fact, it is a fundamental theorem of topos theory that if F is Lex, then its left con extension along Yoneda is also Lex.
Okay, cool.
And so that's why this actually gives you a monad on Lex, right? And So one thing to note, right? So the algebras for this, by the way. So the alg of P um, is, I'm going to define that to be what we could call logoses. Logos. And so I'll note that an algebra for P, so theorem, which is, I'll cite the Lacan-Garner, I guess. In algebra, a presentable and or like a a presentable uh a presentable category C, which is, I'm writing it this way because this notion of presentable just refers to the like as an ordinary category. It's like, so there's a there's a set of kappa small of kappa finitary objects um, which generate C under colimits, but which is a P algebra is a topos. Um, if and only if. And really, it's
Okay,
like
so that's a diff.
alg of P restricted to presentables is the two category of toposes op.
Can I ask, is
Yep.
being a P algebra, I mean, it to be a KZ,
Yes,
right? So
it
this
is.
does like a property of
Yes, it is. So it is, yeah, this is great. If you're a category with finite limits and you admit a P algebra structure, so what does that mean, by the way? You means you have something here, PC to C, some functor like this. And what is it? Well, it's going to be it takes a presheaf, right? And it's going to take, which I'll call a weight, and it's going to send it to the weighted colimit of the identity of C. And we note that the weights are always small. They're always small colimits. And therefore, this is actually always exists. And that's the algebra structure. And so in other words, this is all colimits.
So as long as he has all small colimits, it admits a essentially unique P algebra structure.
It also has to be Lex because it's in
yeah.
Lex, and that's very important. That's very important. So it is as you may know, right? Like that if I have, I'll write it like this because I like to. We have so the PC, yo, we have PC, and then we have this algebra map, maybe, right? We have a map like this. And that this exhibits alpha as an adjoint of yo.
Oh, okay, yeah.
And now you note that this is fully faithful. So we see that essentially C is a Lex reflective subcategory of a presheaf category, roughly speaking, and therefore it's a topos. This, of course, the thing I just said is not size correct at all. Like you have to fix that argument to make it correct, but that's sort of the idea you want to think of. A topos is always, say, a Lex localization of a presheaf category, and if you frame it in this way, you can get that to be true even though the sizes don't quite match up. So,
Okay. So I have a nice theorem here, which says that a category, like, can I sort of recognize which categories are toposes?
Yeah.
Or can I understand like what algebraic structure a toposness puts on a category? And the answer is there's this sort of P algebra structure with respect to this free co-completion.
Exactly. So now I'm going to tell you that. So I'll tell you that fragments of positive logic correspond to sub-KZ monads, submonads. I'll just say submonads, sub-KZ monads of P on Lex.
Okay.
So what does that mean? Well, what it means is basically that if we have one of these, say I'll call it D, then we have that DC or D of or I don't know, maybe.
Well, what does that mean anyway? Like that, so uh,
I'll say this.
what is that?
This is free co-completion. Co-completion. So a submonad here is some co-completion. completion. But it has to be still with it has to still be a monad on Lex. So we should really call it a Lex co-completion.
But so an example here is
So
presumably like something like regular logic.
yes,
Is a particular submonad, which is some sort of lexical completion.
yes, the regular completion is a submonad of P.
Right.
Yeah.
And in fact, there are not that many fragments of positive logic. So you're saying also there are not that many sub. Is that true? Or no,
there are actually a lot. It's just only
there are
some
only
are
some that
popular.
are popular. Okay.
Yeah. But the right way to define it, in my opinion, is this.
The right way
The
to
right way
define
to define fragment is like that.
And what makes one of these what makes a fragment popular? Like are there further properties on
Usually
submonad?
they have to do there's properties relating to what's called the conceptual completeness, and there's also they're sort of indexed by size, and there are historical features relating to other kinds of things. But generally the stopping points are given by cardinality classes, and they corresponding only to the propositional fragments. So like things like actual first fragments of first order logic, and maybe I should say a positive type theory. Really, it's really more correct to say it's a fragment of positive type theory, because
Does logic have a notion of positivity?
yes, it does as well.
Okay.
Logic concerns only propositions, but these concern general construction. So I'm going to give you an example here. Yeah.
So is it claim that step one of the free code completion are also going to be some notion of code completion? Or I mean,
yes, in the sense that, yeah.
Okay. Or is it like we're only interested in those submonads?
Well, I don't know. I think it's true that if you're a KZ monad, your submonads are KZ, but I'm not sure. So I'm just going to say I really mean sub KZ monad. I mean, like it's a KZ monad that's a submonad of this, and the KZ monads are all co-completions. This direction of KZ monad, and so there's a sense in yeah.
I think it might not be, but we can.
What do you mean?
Well, I'm not sure it's really every submonad of a KZ monad, is it?
KZ. Yeah, I've always said sub KZ monads. I just didn't want to introduce the notion of KZ monad to talk about it, but it's sub KZ monad of P, which means it's something that it's a property-like structure that embeds fully faithfully. Yeah. So sub fully faithfully monad.
Right. And I guess we would also classify it as a subclass of colimits.
It's a subclass of colimits. Yeah, it's exactly. So what is, by the way, so DC, right, into PC, right, is therefore a class of colimits on C closed under finite limits because it's Lex, and closed under like colimits of colimits or colimits, etc. As in saturated.
Yeah. So these technical details are great, but I want to bring us back to
better
like
to say that this is a saturated class.
I want to bring us back to this sort of trying to close out your overall point.
So let me give you an example of this, which is the Lextensive completion D, which corresponds to coproducts. But it's not just a coproduct completion. It's not FAM, because we actually let's say we only took coproducts of representables, right? It's not true that finite limits of coproducts of representables are necessarily representable, I think. I have a tendency to be wrong about these fine points here.
Okay, you're sketching a picture about conceptual modeling.
Yeah.
And so what I hear is that like there are certain modeling languages which are sort of fragments of positive logic, and we can study these through studying these sort of aspects of topos theory, essentially through the sub KZ monads of the free code completion.
And the main point is that these things are what I'm going to call concepts. So they are concepts. They correspond to one. They correspond to certain kinds of queries, and they correspond also to conceptual models.
So you're saying you pick a particular fragment of positive type theory.
Yes.
And like that is a particular class of concept/conceptual model.
Yeah. And um, we can talk more about like um, how this might work in practice. In practice, you don't want to say necessarily fix it all up front, but I'm going to tell you that that there's like essentially um, being able to form finitary inductive types is a really good big tent.
So,
Together with extensivity. So I'm going to tell you the other thing we missed something important with this Lex theory, which by the way also the Lexes also correspond to so-called generalized algebraic theories or GATs, and there was GATLab. But then in both the Algebraic Julia project with CatLab and in GATLab, which are all based on these sort of ideas about modeling, David Spivak's ideas of modeling. They both needed to use these things called attributes, and attributes are in a yeah, sorry.
right. So there's a lot to introduce here. We're not going to
Yeah.
get through it all in
Okay.
this 1.5 hours or so. But I'm trying to like what you've done is we have this table here,
Yeah.
and you've introduced a whole lot of sort of fragments of logic between, I guess, relational databases and topos theory
Yeah.
that play out the story of sort of conceptual models.
Yeah.
Right.
And so,
But I
yeah.
don't see yet you have been making argument for like why. So you said that there are a lot of
Right.
different flavors of this sort of modeling, like modeling environments that you can step through between, again, categories and toposes. But I haven't seen yet the argument that says like these, and in each flavor of this, you have these, equivalents of syntactic sites, maps of syntactic sites, whatever,
Right.
objects, geometric morphisms, different flavors. But why are these things actually these sort of modeling affordances?
So
I have the argument in terms of
I think I
conceptual
need to
models
like
theories.
maybe I should have just started with the type theory instead of the topos theory, because the type theory makes it a lot more clear, in my opinion, like why this is like good for modeling. But like the I like the so GATs. So you started with you started with O logs, but that wasn't strong enough, so you went up to GATs.
Right.
But you also, before you went up to GATs, you actually did another thing to O logs, which is you added attributes.
Right.
And then you had to add attributes to GATs.
Right.
What you end up there is a particular fragment of geometric logic, in my claim.
So the attributes are again that's not orthogonal, right?
So if an attribute, if we go all the way down again, so I don't know. Or like, should I not? An attribute corresponds to it's instead of being a foreign key, it's actually a value in your base type theory. Like it's an actual float or an int or something, or maybe a list of some things, right? But it is a list of some basic types. Like it's a basic type. It's something in your outside external programming language, right?
Right.
And it's always considered to be the same in every instance, right? As in that type is always considered. It's not like everyone chooses their own notion of float. No, we intend that same notion of float.
Right.
That corresponds to the extensive fragment. If you add to that essentially quotients by equalities, you basically are at geometric logic, roughly speaking. And so this is sort of the argument for using this, is that like really like you're already actually doing this in this way of like these attributed GATs. And then I can tell you about how do we go about, for example, doing this computation Petri nets to ODEs to actual computing them, how that can be separated out. So that the things that you have the syntactic sites, and then you take the sheaves on them. And what do you add when you add sheaves? I'm sorry, this has gotten such a mess. But what do you add when you add sheaves? You add so syntactic sites, they have certain finite limits and certain co-limits. And these allow you to express certain kinds of models, conceptual models, right? But the whole topos of sheaves has two other kinds of constructions that are really important. It has function spaces. It's Cartesian closed out of nowhere. It's Cartesian closed. And that's not true for a general P algebra, by the way. It's important that it's presentable, right? Which is to say, which is like, you have functions, and you have sub-object classifier, which is, so you have an internal notion of predicate, and it's sort of, and these are impredicative. You can quantify over them, right? So in other words, you get to do, and you also have other things. You have terminal coalgebras. You have terminal. Now, you can sort of characterize the colimits you have in these various syntactic sets as initial algebras for endofunctors, but the terminal coalgebras you definitely don't have. And what those correspond to are behaviors of dynamical systems. And
So
so
okay, so
you can,
what I'm hearing is like,
in other
you
words,
know,
solutions of data.
as you move up this logical hierarchy, you get sort of all
No.
this emergent stuff.
No, it's in fact, it's the difference between the positive
Uh,
side and the negative side. Functions, subobject classifiers, terminal coalgebras, those are all
the negative.
negative.
Right.
They are defined by destructing them and
Uh-huh.
observing their behavior, right? You observe a function by applying it to an argument, you observe a stream by looking at a
Right.
finite prefix, and you observe a type by.
So are you making an argument to say you have to move towards topos to have a rich enough structure to have these negative concepts, or that these negative concepts, so in some way, why is this area empty?
Because databases are all about data.
Right.
And
But
so there's just nothing in the computational
okay,
data. But oh well, yeah.
what about if we don't,
This
these
is
databases and
where
topos theory don't sit in the same thing.
Programming.
What about
Yeah.
like if you just look at regular logic or something, right?
Right.
The theory of regular categories.
Yeah,
Would
yeah.
that have a negative?
No.
No.
Yeah,
So
so this is the main point: is none of the fragments of positive logic have
Right.
negative types.
Okay.
They are characterized by not.
Right.
Um,
So okay. So
and
you're saying
but the important thing is that when you go to implement
Mhm.
when you go to write down the practical model, you have to use actual computation. You have to write actual functions. And that's where you suddenly find yourself in need of a world where you have negative types like functions and streams. And like the solution, if you think you take your Petri net and you compute the ODE out of it, that's totally in the positive world. You've just shuffled data around. Now that is a kind of computation, I should note, and it in fact does correspond to a kind of geometric morphism. Like a map of syntactic sets induces a geometric morphism.
Right.
That's why I say translations live sort of in both sides. But when you go to take the ODE and you compute the solution, what is the solution to the ODE? It's a stream of values that you compute, right? Usually you take from that stream a certain finite prefix, so you actually like stop writing your graph. But in principle, you're computing a stream of these things, and you do it using general functions, general computation, and it's not just shuffling around.
Okay. So you're saying,
yeah.
so to summarize, you're saying, we have a categorical theory of data, and what you're after now is a categorical theory of data and computation.
Yeah.
And when you have a categorical theory of data and computation, or when you have a theory of data and computation, you have a way of doing conceptual modeling.
Yes.
And you're arguing that topos theory is a categorical theory of data and computation.
Yes. Yeah. And in fact, the distinction between data and computation is really at the heart of topos theory, this distinction between positive and negative. So it's not just that it can handle it, it's that it fits it like a glove. It's really, really closely related. And then you can, the other thing is that you can have putting it all in one place is a nice way where you can type check all of it at once together, so that you aren't in a position where like suddenly you drop off giving guarantees about your modeling. And that's something I haven't talked about is also how compositional modeling works in here, but it works really nicely. And so you have this thing where you can talk about compositional modeling and then the implementation of your model.
Composition in the sense of like in a particular doctrine of composition, like colimit.
Yeah, sharing variables.
Okay.
Yeah,
But
it turns out, yes, which is the same as
which is a particular. So in other words,
Yeah.
basically every topos gives rise to a double operad in the like.
Yes. Well, yeah.
Okay.
Yeah.
And here, so you're telling me basically you're making an argument for how, like, as you explore notions of data and queries, actually you basically find yourself at a topos as you sort of have richer notions of querying, and you find yourself at the topos structure, and so therefore, like the negative structure, you may as well.
So yes,
So you didn't introduce the negative structure.
Yeah, I didn't. But
at all.
it is true that the negative structure appears by the adjoint functor theorem for presentable categories.
Right.
And so there's a weird sense in which, mathematically, it is true that in fact all the negative types are positively definable.
Right.
That's sort of the content of the Giraud axioms for toposes, but or the fact that they work. But the fact that a co-complete elementary topos, or like a presentable elementary topos, and a presentable category satisfying the Giraud axioms describe the same class of objects is saying essentially that these negative things, the type that defined elementary topos as sub-object classifiers, function types, um, can be captured by the positive stuffs if you know that everything can be being presentable says you already know that every object can be presented by a colimit. So it's a sort of a special case. But but when it comes to practically doing this, they end up being practically represented in completely different ways. Namely, one is an inductive type and the others are sort of co-inductive types.
Okay. And how does your picture handle double categorical structure? So in many cases, we've observed that like a modeling language is inherently categorical, right? So you don't just have, as a categorical structure, you don't just have a sort of category of models, you have a two category of models, right? The models are category like set-like. How do you see that coming in?
Right. So you do get you get a category of models, and you don't naturally get a two category of models. However, you can always describe the one you would get. So, for example, to connect this to double theories, the actual mathematics of Cartesian double theories actually tells you what is the correct notion of the formal category theory, which is actual virtual double category of your models, right? Which is even better than just a two category of models. It's the actual formal category theory of it. You're not going to read that off of this theory. Nevertheless, all of the Cartesian double theories are lex. So they're all presentable in this. So if you go and use that as a guide, you can at least represent that all here. And so but it doesn't tell you how you should. It does not. This point of view does not make the assertion that the models are themselves categories. They're like completely unconstrained in that way. Another thing I'll note is that the modal double theories, which make use of monads and are what is used currently in Calculab to write down Petri nets, they are very much in the positive fragment. Because they use not just the finite limits that you need to express, well, in this case, you don't really need anything. It's a sort of otherwise a simple one. But they also use the list monad. And the list monad is a inductive data type. So it's in the positive fragment, which I really should have probably explained before doing this.
Right. So sort of these aspects of double categorical logic that appear in Calculab don't explicitly appear in this underlying formal thing, but they are representable. Like
they are at least representable. And
I mean, if you are looking for unifications, maybe my last question until we wrap up in about time, does this point towards like a sort of double categorical version of topos theory as a unifying way, or is that not something that would
That's not something I'm thinking about.
Would it be like sensible to even think about that, or is that actually quite an orthogonal direction?
I don't. I would say that's orthogonal. So the thing about it's certainly true that double categories are in double categories are the right way to do. I think I would say like two categorical algebra and formal category theory, specifically formal category theory, and also they are the right way to find the correct kind of representability that you need to see that compositionality results in operatic approaches to systems theory are in fact representable by morphisms. Like you need the double aspect for that. However, this again, the translation of mathematics is not the most important thing. The most important thing is the idea that you can give a type. So I really should have just done the type theory. I tried to do this without type theory. It doesn't really work without the type theory.
Oh, well.
The main point is that every topos is a model of Martin-Löf type theory. And then you can actually give a type theory where you also are allowed to say in your topos, actually, here's a theory, and then you can jump into the logic of that one. And so you can give a single type theory for all of these, or at least that's what Mitchell and I are proposing to do. And the idea of that is then that you actually are able to have a single programming language, essentially, that can check all of these aspects of modeling, right? So it doesn't it doesn't tell you what to do with the model. It doesn't in its own format tell you what to do with the modeling, but it gives you an actual sort of practical way to type check your modeling system. And even to write, if you are happy writing things functionally, to even write code, like actual, computations concerning your modeling in the same system. And that's really why I like this.
Cool. I think that's an excellent point to wrap up.
Cool. Thanks.
Cool.
Yeah.
Thanks
Sorry
so much.
for the mess of it. We'll try again and it'll get better.